Again, there are a couple of seats down here. Next speaker, Professor Matijevic, also from Clarkson University, was Kendall laureate in 1972, and I believe the name then was Clarkson College of Technology. That's right. The title of his Kendall Award address back then was Colloid Stability and Complex Chemistry, and today it's Mona Dispersed Colloids, Achievements and Problems.
Thank you. This morning I got some statistics from Art Adamson. I got my award 5 years ahead of time, and now I'm 1 year behind time. So it's interesting to see what happened in INTRI. Complex chemistry I used to show how to make colloids and how colloids interact, rather than take a straight physical approach, which has been very common in the literature. My first slide shows the first slide I showed in 1972, and it was supposed to introduce for the first time monodispersed, quote-unquote, colloidal particles of metal oxides. This was chromium hydroxide, zinc basic compounds, Aerosol oxide, and 2 copper oxides. Obviously, at that time, we were very proud of this achievement because nobody had prepared any such uniform inorganic particles in the family of metal oxides. As a matter of fact, it was a curiosity, and the only, with few exceptions, which Milt mentioned, sulfur, sol, and so on, we had very few inorganic uniform colloidal dispersions. And people wanted to have them to evaluate properties of matter, optical, as we heard, magnetic, and so forth. As a matter of fact, the only really good materials available were polymer lattices, but despite this beautiful uniformity and sphericity, they could not be used as model systems for pigments or for corrosion or for catalysis and so on. There are 2 aspects about this slide I'd like to mention. First, I would never publish it today anymore. This is nothing that we would be now interested in producing. Second thing about it is that at that time we felt that such uniform particles are essentially important for academic reasons to evaluate properties of matter, and little could I hope that ceramicists will discover colloid science and that fine particles now are so essential in modern technology that pigment people would like to have uniform particles to have reproducible pigment. Some magnetic recording materials depend on uniformity of particles, and I could go on forever in giving examples. So what I'd like to do today is show you what progress has been made. And I'll give you a picturesque talk in a true sense of the word, because I'll show you lots of pictures. But as it always happens, once we learn more about the subject, we want to get more sophisticated answers. So we achieve certain things, and then we create problems. As a matter of fact, we try to solve the problems. So I'm going to use this opportunity to point out to you where work needs to be done. So it's not good enough just to make these materials. It's important that we answer certain questions. Some have been answered. Some need to be answered. Well, we have essentially worked with 3 techniques, and I won't have time to go into any details. The most common is precipitation. And I would also skip phase transformation and mention aerosols. By no means are those the only techniques available to make uniform particles nowadays, like Stig Friedberg and Clarkson using surfactant solutions to get unique particles and so on. I'm going to just mention area of interest to us. Precipitation being uncommon, and all of us know what are the fundamental principles. We have to carry out this complex chemistry of solution in a kinetically controlled way to produce as short a burst of nuclei as possible and let these nuclei grow. Lots has been written about it and so on, and I won't go into details. I just want to show if you conduct this solution chemistry properly, you can make aluminum hydroxide like this, perfectly uniform, spherical, and amorphous. There are many examples of such amorphous particles. I'll show one more. This is silica. Some of you might substitute it in your thinking by latex, but indeed it's an inorganic system. This is the latest material that we just produced by a modified technique, and it takes no more than 20 minutes to make it, and we can make pounds on a laboratory bench in one morning, such material. So here is the difference in quality between 1972 and whatever 90 it is now. Now here is cerium oxide. There is a substantial difference between the first two slides and this one. They all appear spherical, they are spherical, except the first two materials were amorphous, and this is crystalline. And for a long time we wondered, how can one prepare by homogeneous precipitation a spherical crystalline material? Now here I have a little lapsus. It's not essentially crystalline. We have X-ray pattern of a known crystal, and that is a major difference. Before I return to this, I'd like to show you somewhat different particles, also of cerium oxide, and somewhat different case again where we have this rod-like and spherical particle mixed. And what is the difference in preparation? Use the same chemicals, sulfuric acid, cerium sulfate, warm-up solution. And we have here in this range these uniform particles. Symbols are characteristic. Here are spherical particles, here are rod-like, and they're mixed. It just shows the sensitivity of the system to chemical composition of solutions. And that's one of the major problems now, how to relate the chemical mechanism of the particle formation to the nature of the particles. Before I go to this problem, I would like to now go back to this question of spherical particles that have crystalline characteristics. That's a time-resolved series of electromicrographs, and what you do form first tiny particles in 30-40 angstrom range, which with time aggregate to give you these uniform large spherical particles. I have no understanding of it, but Rees claimed that it's very easy to understand. He promised even to write a paper on it. Have you done it? But he might be able to comment on it. Indeed, let me now make a very general statement. A large number of spherical particles that have crystallinity of known minerals are all composite. That none of them is a single crystal. We can start with an amorphous particle, calcine it, and get a uniform crystalline material, but not directly by homogeneous precipitation. The problem next that needs to be addressed, which we don't know anything about, is the particle shape. What controls particle morphology? We have absolutely no fundamental principles on which we can build an answer. We can always rationalize, we can produce particles, go backwards and say, they are spherical, or they are, I don't know, this or that, because what we've done. But if you ask me, can you make a cubic cerium oxide, I would say no. And this is one of the, I think, fundamental questions, which is not only of interest to colloid science, of interest in mineral preparation, mineral growth and stone formation, and many, many other areas. And let me illustrate this by a number of slides. First of all, you can change particles with the same chemicals, just changing temperature a little or concentration. One very important parameter are anions. In mind of lots of people, it's not really essential what salt I use. If I want to precipitate iron oxide, what difference does it make if I start with ferric chloride, nitrous perchlorate, sulfate, and so on? Nothing is further from truth. And let me show you examples. Iron is very difficult to control. As a matter of fact, you have to go down to pH 1, and you still can make oxide. As a matter of fact, you have to go to pH 1 or 2 to make uniform particles. And here is such an example. Those are really beautiful crystals of jarosite. You have electron scanning and replication. You can, those are not just to make 5 particles. You see it's a large population, truly uniform crystals. You can change morphology. And then you change anions. With nitrate, you get hematite spherical. The previous were jarosites. Here we have also hematite, which looks different. If Dr. Scheiner is here, he's here, he made it. That was during our bicentennial. I told him make a real good particle to celebrate bicentennial. He came close, but did not really succeed fully. Just to make 5 particles, you see it's a large population, truly uniform crystals. You can change morphology. And then you change anions. With nitrate, you get hematite spherical. The previous were jarosites. Here we have also hematite, which looks different. If Dr. Scheiner is here, he's here, he made it. That was during our bicentennial. I told him make a real good particle to celebrate bicentennial. He came close, but did not really succeed fully. Now, you might say, okay, that's the anion effect. Now, here we have 4 cases where we have the same anions, all ferric chlorides. In changing slightly conditions, you can make perfect cubes, spherical particles, these strange particles. They are hematite, and those are acagenite, beta FUOH. So what I'm trying to press upon you, we can do all kinds of things, but we cannot predict it. And that's a fundamental problem that I think the young generation has to address. We are too old to solve it. Now let me show you some other examples. We can do practically everything. This beautiful hematite, and that's hematite, and this is hematite. As I say, that might be my next Christmas card. And then that's hematite platelets, which we recently produced, and we can make cubic, so we can make particles of all kinds of iron oxide, of a variety of chemical compositions. And here is hematite disc-like. I've forgotten about this one. Now, next problem. We like to make composite particles to change properties. They can be internally composite or externally composite. So here we have cerium, zirconium oxides and cerium yttrium oxide. You would normally expect me to make copper yttrium and copper lanthanum oxides, and here they are. And now we have very interesting, again, problems to resolve. Okay, you start with a solution where you have 1:3 ratio, whatever you want, copper, yttrium, and so on. Will your particles have the same ratio in the solid state? That's number 1 problem. Number 2, will this distribution of these metals be uniform throughout the particles? Well, we have answered, or are trying to answer some of these problems. All relatively new work. Some has not even been published yet. And here we have, for example, yttrium copper system, and that's the solution composition, and that's the percentage of copper in the solid. And there is a chemical composition that we can calculate that fits these experimental points. More interesting is the following. Here we have particle growth of this copper yttrium system, and what you've done is we've quenched the system at these different times and analyzed the composition. And what came out is very fascinating, I think, that the ratio of copper to yttrium or copper to lanthanum changes. At first you have excess copper, and then later we have excess. After long enough reaction time, our composition total equals to that in the solution in terms of molar ratio. What it really means is that our particles from center to periphery differ in composition. So we have nucleation stage with primarily one oxide, and then the second grows onto it. When you calcine this system, then you get uniform, well-defined composite oxides of known stoichiometries. Well, that's interesting, for example, for catalysis, where if you want to enrichment the surface of one metal against the bulk, and many other applications. Here is the next way one can approach. We can coat one particle with another particle. This can be done for two reasons. First, maybe the material can be scarce or expensive. So why to use the whole particle? We can use core of an inexpensive material, put the precious material on the surface. Second reason is we may not be able to make a particle of a given morphology. As I told you, you have no way to predict it. Well, you can take a core of a given morphology, desirable, and then coat it with the material that we're interested in. Let me show you here a case. This is a nice hematite. That's yttria, prepared separately. Incidentally, you can now make this yttria in a continuous process. We have chemical engineers in my research group who are really working on scaling up problems and so on. We can make, over a period of 24 hours, continuously this yttria of identical properties in terms of size and shape. If you now put this on this, that's what we get. Perfectly nice coated particles. We can control the thickness of the coating. This is not a single system. Quite recently, it's still unpublished. Oh yeah, here is the reason why we want to do it. That's our, this is microcalorimetry. Calorimetry, you can use DPA, other techniques. This is the core material. This is the coating material. And that's what you put this on this, you get that. So your surface characteristics naturally correspond to what's on the surface, as one would expect. On the recently unpublished work, we used now latex and coated this yttria. We can now have different situations here. We have a uniform coating, we have spotty coating, we have such yttria in blobs on our latex, and we have a mixed system. We now fully understand the mechanism, and that's the process, kinetics again. This is the aging time. We use this with urea in the system. So if we have large amount of urea, we form tiny yttrium basic hydroxide of opposite charge, very easily absorb and form a uniform layer. If the process is slower, our yttria particles glow larger, we get these blobs. If they are very slow, we can mix systems. So all of this starts to make sense. We can now do some other interesting things. Now we can make such system and we burn out our latex. And if we burn it out, we get hollow particles. This is all unpublished. Here is the paper on review. We also can now reduce the latex inside. Then we get carbon particles coated with yttria. So we have a conducting core and non-conducting coating, which has a great deal of interest. We have now another case which I've just again submitted for publication, where we now absorb, say, pyrrole monomers on iron oxide particles. And now this iron oxide plays a double role. It's a carrier, it's core material, but also it's a catalyst, and catalyzes the polymerization. So we polymerize these particles of pyrrole on the surface. Now we have a conducting surface and non-conducting core. Here is cerium oxide. What's interesting about it, we did not invent this polymerization of pyrrole, but everybody else has done either by electrochemical catalysis or with ferric ions. We have no ferric ions. It's really a surface polymerization. Now these things are not really limited to oxides. We can make practically any material. This is zinc sulfide, which has exact characteristics of sphalerite. This is lead sulfide, galena. In this case, you have obviously crystalline forms. We have selenites, phosphates, carbonates, you name it, it can be done. Here is a copper oxide, and this I'm showing for artistic appeal. And don't you ever ask me why anything like this can be done reproducibly, but I assure you it has been done over a period of time by a number of people, and it is reproducible under a constrained number of conditions. And now with all of this experience, we've been able to produce very much more complex systems. Like here is, for the first time, you see a spherical barium titanate. We can make lead titanate. We are making niobates. They are now in print, so new material, and all of you who are in different industries know that they have all kinds of interesting applications. In this particular case, we decompose a complex cation and a complex metal and complex anion simultaneously, and if you control it properly, again, phonetically, you can make such perfect spheres. The last technique that I want to mention here is the aerosol technique. Now that's upside down. Right? 3 times I double-checked it not to have it happen. Aerosol in itself is a very interesting approach. What we do here is we use droplets of one reactant and take a vapor of a co-reactant. Now, why would that be so an interesting approach? First of all, the spheres, the shape is predictable. Droplets are always spherical. We have yet to see. Size is predictable. If you know the size of your original aerosol droplets, you'll know the size of your final particles. The purity of material can be phenomenal, and the reactions are very fast. And now if we have good spray techniques, you can produce composite system of predictable, again, composition. What you put to your particles will come out in terms of metals, so you don't have to worry about the final composition. In principle, one can do it very easily. We flow down, this is not what Milton and I have done this some years ago, the actual original the generator, where you flow down a liquid. This is just a temperature control, you condense it here. Now the novelty here is that we now introduce a vapor in a reaction chamber of any kind. We have all kinds of designs, and out comes your product. Let me give you a few examples, and then I'll tell you what the problem is again to be resolved. Here is titanium dioxide obtained by such a technique. You start with an alkoxide, say ethoxide, protoxide, and so on. Expose it to water vapor, and out comes your titanium. Here is tin oxide. Now here is tin tetrachloride, and used ammonia as a reactant. How fast are these reactions? Well, we follow the kinetics of these processes. Since they are sufficiently uniform, we use the aerosol techniques for sizing and refractive index determination and so on, again, by a technique which Milton and I developed many years ago. Liquid aerosol is brought in here. We can evaluate its size and optical properties. Then we can introduce water vapor here, and this is our reaction time, which can be exactly calculated. And here we pick up the signal, which you can interpret in terms, again, of size and composition. Then we can cut it down the tube or pull it down and have longer reaction time. Let me show you such a set of analysis with titanium ethoxide. This is the original signal, and those are signals after different times, which you can interpret then in terms of refractive index change and the volume. And here we have titania solid particles. Here we have liquid aerosol, and the whole process takes 300 milliseconds. That's all that it takes. We are not restricted here to inorganic systems. We have now organic system. You know, it's very difficult to make latex in large size, 30 microns. I went even to the space shuttle to do it. You can buy it about 50,000 times the price of gold. A few samples. That was done with the labor of a poorly paid graduate student in a hood. Only take a droplets in this case of divinyl benzene in this case, use a vapor initiator like trifluoromethane sulfonic acid, and you polymerize it. You can actually make now by Aerosol Technique polystyrene, anything else. You can also make polymer particles that cannot be done by conventional techniques, like polyurea. Here we have a direct copolymerization. We make droplets of diisocyanate and react them with ethylene diamine. There is no side product. The whole thing is just polymerized, and you have your polyurea. We can now introduce also an inorganic vapor here, and at the same time polymerize it and hydrolyze it. Now you get organic particles loaded with inorganic particles. Actually, we can do even more. We can now produce titania first, then in a vapor phase, in a continuous process, a tandem reaction, we can deposit diisocyanate on it, expose the whole thing to ethylene diamine, and get now titania coated with polyurea. The whole process takes about 1 to 2 seconds. So if it's such an ideal system, why doesn't everybody jump and do it? Well, here again, the major problem is to make sufficient amount of uniform droplets, you see, and that is a technical problem. Right now, we can make lots of this stuff, but we cannot make it as perfectly uniform as we want to. In many ways, for scientific reasons, we can make plenty, which reminds me when they asked Deryagin at one point, so how much of this polywater did you make? And he said, enough to publish 26 papers. So we can make lots of this stuff, enough of this stuff to publish 26 papers. But the real challenge is to find mechanical means to produce large number of uniform droplets. Since reaction is so fast, we have a really very exciting technology. Incidentally, we're already making larger quantities, as I say, but not as uniform. Like we can make cordierite right now, of interest to ceramic people, by using proper mixed oxides. Well, that in a nutshell is what I tried to show you. The science is exciting, I think. The materials can be used for all kinds of investigation, relate optical properties, size, shape, chemical composition, magnetic properties, absorptive properties, you name it. We can make lots of interesting products for all kinds of applications. What is really exciting, that people finally have recognized the significance of fine particle science. How do I know this? There are 2 reasons. I'm getting money to do it, that's an important reason, but when you get cartoons in scientific literature to refer to a subject, then you know you've won. And here is from American scientist, a cartoon which appeared last summer, where we talk about particles, particles, particles. Thank you very much.